So before Param will start teaching the real things, I'm going to talk just a little bit about, my general philosophical asides. So what is that we're trying to do? We're trying to write pieces of code, which are good pieces of code. And how do we try to define goodness? What is this criteria for goodness, which we're trying to sort of discover? And the criteria for goodness is that things which we write should behave the way people expect them to behave. That's sort of would be good. You write a piece of code, and everybody else will immediately say, this code behaves the way it should be. And let us look at what it sort of would entail. It would entail, for example, that if we produce new types, they will work with old types. For example, if we produce a data structure, this data structure will be able to contain whatever other things we got. For sure should be able to contain all the building types. That would be sort of nice. But then we would want this data structure, whatever it is, when we concoct it, to be able to be contained by any data structure which will come in the future or which already exists. So that we want this notion of regularity. Somehow things would just work nicely. Yes? And one of the ways we want to derive this notion of regularity is to say that we're already given a bunch of good examples. And these good examples are building types. Because people seem to be happy with them, so we could use them as the beginning of our edifice building activity. Yes? And when we look about sort of what unifies all the building types, what do they have in common? We come with a set of requirements which is pretty much the ones which we need. It's one way of sort of thinking of what we're going to teach you is that this is an ultimate generalization of building types in C. We will provide sort of a way of expanding them forever and forever while keeping these basic things.
And similarly, not just,
But doesn't it come to conflict with your statement that it's like a Pandora box you're opening? If things are so simple, and if things were very straightforward, there's less or little or no room for making an abominable, dictionaries of hashes of trees of dictionaries. Whereas if you provide this complete transparency, you're encouraging in a way that.
Yes. That is, for every goodness, there is a corresponding badness. If you give a person a really very sharp knife, he could cut off a lock of his hair, or something even more important, and people do. It should not prevent us from building sharp knives. That is, people need to learn to program responsibly. In the sense they should understand the data structure and algorithm implications of what they do. But it is, in some sense, would be good. Okay, let me give you an example. Some of you remember that I sort of claim that we are all mathematicians. Those of you who started a long time ago with the Journey course. And when we look at how mathematicians do things, not even intentionally, they create the same sort of structures. They say, well, we'll have integers, or natural numbers. Then they somehow observe that, well, minus doesn't quite work. 3 minus 5? So they come with a mechanism for doing that. They discovered that if you give me a semi-group, I could first extend it to monoid always, and then always instead extend it to a group by sort of, there is this wonderful mechanism which always would allow me to do that. Then they come and say, well, but division doesn't work. So they come up with a way of extending their numbers so division will start work. They get rational numbers. But again, they come with a mechanism which will take two things from an integral domain, some kind of a ring, and these pairs of these elements will then give you a field, things closed under division. So we get rational numbers. But then they sort of keep going. From rational numbers, they get polynomials.
I mean, and the point here is the extensions are such that everything you knew worked with numbers still works with rational numbers.
And
but you can do more.
And the same construction things. For example, you get polynomials. And of course, you find yourself that you have an integral domain, but division doesn't work. Two polynomials do not necessarily divide. So they say, oh, well, we already learned how to take pairs of things, of integers, and construct rational numbers. So we will do exactly the same and construct rational functions, a pair of polynomials, and with exactly the iteration. So you create this, and you could go on forever, by the way. They don't, they stop. I mean, nobody goes forever because we haven't got enough time. Nor there are particularly interesting things there. But this ability to use the same structure, to use this notion of overloading. For example, they invented the notion of plus many, many thousands of years ago. And then they tried to extend this plus to newer and newer classes of objects while keeping the fundamental properties of plus the same, sort of a conservative extension. Yeah? So we should try to do the same. We should try to keep familiar set of interfaces. And let me jump ahead just for 1 second before I give things to Parham. So when we sort of look at what are the fundamental operations on which programming is based, we discover that first of all, its ability to copy things. As Parham always says, what do we do here at A9? Oh, we copy bits from one place to another.
For the most part.
For the most part, right? So we could copy things. Something mathematicians don't really do. But copy for us is. So we need to know what does it mean to copy. Huh? But in order to figure out what is copy, we need maybe to know that copy means to construct something equal to the original. Seems to be a reasonable definition of a copy, which means that we need to figure out what does it mean that two things are equal. Yes? But then we could do that. We also want to be, allows us to be able to find things. I mean, if you have equality, you could look for a bunch of things, whatever it is, and find the one you're looking for, sort of a notion of linear search. And then, finally, we occasionally want to find things fast. And what is the most reliable way of finding things fast?
Guessing.
To sort them and then use binary search. And that requires that we have some notion of ordering. Right? So that gives us the things in which sort of define the notion of regular types. What we could do. We could find things, we could sort them and put them in. So I mean, it's and when we look at what I just named, pick a building type. You could do all of that. You could, for all building types, you could copy them. For all building types, you could compare them by quality. I'm not going to talk about some weird floating point values, just so that not to confuse, but I mean, for normal values, values which are supposed to exist, you should compare them for equality. And amazingly enough, in some sense, again, I'm lying a little bit, but all of the building types give you total ordering. It's in practice, it's always true for pointers, but not in theory. This is this paradoxical thing, but practice is stronger than theory. It's usually the opposite. In practice, of course, you could take any pointers to integers and compare them with less than. And nothing bad will happen. But of course, the C tells you you cannot do that. I don't know how many of you realize that? How many of you realize that? Oh, not bad. Not bad. Okay, so why could we do it? When can we do it? Not you.
Me?
Yeah?
When they point to the same range.
To the same array. Yes. Very good. But of the standard committee, C standard committee, a long time ago said that this is defined only when they point to the same range. Fortunately, Intel doesn't know about it. It does the right thing anyways. But it is illegal. So we could assume total ordering for all built-in types. And then where Param will lead us is what do we do with total ordering, what total ordering is, and other practical things.
And I mean, just to add to that, Alex talked about containers, but another thing you want to do with any type you define is to write functions that operate on it, and write algorithms for it. And so the kind of algorithms you would write for an array, for example, you might want to write for whatever new thing, or for whatever you write for an int, you might want to do with whatever. And so that's the other.
So we can't assume total ordering for floats, right? It's not a number. So
Yes, I said ignoring, I specifically mentioned, I have this room full of
I
witnesses.
heard it too, but I mean, you said it, but then you said we can assume it, okay.
For all the values which make sense. Yes? Not a number, of course, does not allow us any meaningful operations, because if something is not a number, it's not equal to itself, it's not equal to itself, it breaks all the laws of logic, mathematics, and everything. William Kahn, he used to be a professor at Berkeley. Talk to him, don't talk to me. Again, it causes many, many problems, and we could discuss them. But let us right now let us just make the following formal solution. We'll declare certain things, singular values. And we'll say that all the logic equation or otherwise stops working on singular values. So if your type contains singular values, axioms do not apply. Nothing applies there. Singularities, It's like when you go into the cloud and live there with Sergei Page. Pretty much a description of hell. All the top minds, Larry Ellison, Sergey Brin, Jeff Bezos, communing together in the cloud. I think Anil might get there if he sells his collection of knives.
But then how will you protect himself?
With virtual, he needs virtual knives.
So I think what we need to do really is to start writing code, and we'll see all of these things in practice. And I think that will probably clarify and crystallize them in a much better way. So we were writing min when we last stopped. So let's try writing min.
Do we have a specification?
Maybe we should write one. So let's start with something straightforward. Min for integers, min for two integers. So we want to write something. So yeah, why don't you tell me what you type? You want to write a specification?
I want to write a specification.
Okay, let's write a specification.
So I would say, given two things of the same type,
No. Actually, this is good. Let's follow it.
okay. I mean, I want
But I'm allowed to ask a question. What are things? Do you mean values? Do you mean objects? Do you mean what?
instances of some type.
Instances mean value or object. These are things known to humankind. Instances? No, not really.
I would say objects.
You would say objects. You want to say objects. Given two.
I said things, right? It's an object. Given objects, they can be of the same type, and
Okay, let us stop here. What's the difference between value and an object? Jack, could you help us there? Just tell us what you think.
Sorry, I wasn't expecting to get this.
Ryan? If you say, I don't know, say that I don't know. That's a perfectly good answer.
When I think of an object, I usually think of something on the heap.
If it's on the stack, it's not an object.
Me too, yeah.
Yeah.
Can you say that the value is a representation of an object?
You say object can have another object inside.
Value seems more like a primitive.
An object has a value.
Object has a value, that I would agree, but what is, I mean, yes.
The object's value can be changed. The value itself.
Value cannot be changed.
Object
Right.
is a-
Anybody, our notion of value, like 3 is a value, right?
Yeah.
So,
3 cannot,
Yeah.
you cannot say, let's make 3 to be 2. That would,
But the object can have
different
different
value can be changed. The value itself is,
So the value is an attribute of an object?
it's the value of the object.
why do you guys want to be so philosophical? Why don't you try to think practically?
An object has an address.
It's a sequence of bits in memory. Yes, in memory, that's what an object is. It's, and obviously you could change this sequence of bits. The sequence 1, 1, 2 bits is 3. When you put it in some location, it's an object.
so the value is the interpretation.
No, interpretation, well, value is an interpretation of sequences 0, 1. You say that, this sequence is an integer. This sequence is a floating point number. This sequence is a color. This sequence is an address. But it's disembodied sequence of ones. Right? They need to live someplace. We have to once and for all. There are all these people who do functional programming where things do not live and there are no addresses. But let us just restrict ourselves to machines you could buy, fries, and these machines, these bits reside in some addresses. So that's the simplest way of thinking about an object. It's a value residing in memory. Anybody? Problem? I think it's a value. So, what we say that according to Hernan, given objects of the same type, what do you do with them? I don't know.
Given objects can be of the same type, and some predicate defining the order.
And some predicate, do you mean any predicate?
Well, one that defines the order that
That what?
we care about.
And like total order?
partial order.
A partial order.
Partial order.
He says partial order. Let us see. Let us see. They all say partial. Say partial order. Did you say partial order? Defining the partial order. No, 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 you're not allowed to look. Too late. Too late.
No, but before I write anything down, I mean, you said partial order. What is a partial order?
He said partial.
I said, well, so there's, we don't want a partial, we don't want there to be incomparable elements in archetypes. So it's defining an order on T, and a partial order though would have incomparable, right? Saying that basically for any two elements, they're either ordered or not.
What is a canonical example of partial order? The one which is very easy to remember, and you should sort of test every time somebody says partial order against that.
Pecking order.
Actually, mathematically, the best way, and that's when mathematicians sort of came up with the notion of partial order, there are two canonical examples, but the easiest for most of us to remember is there are no parents in mathematics. Well, there are occasions, like Euler had 18 children, but this is true. Less than Bach. How many children did Bach have? Johann Sebastian Bach. Nobody knows. You don't know. Everybody. Okay, since we know that PDQ Bach is the 23rd long-lost child of Johann Sebastian Bach, from that it follows that how many non-lost children? 22. Okay, you see, you're good at math. He actually, he got some degree from a junior university in mathematics, so he could do 23 by as well, just like that. So okay. So the example which is very useful to remember when we talk about partial order is a subset relation. Subsets are ordered. Obviously, one subset could be one subset could be a subset of another subset. Right? For example, subset 2, 4 is a subset of a subset 1, 2, 3, 4. Everybody agrees? Mm-hmm. It also so happens that there are subsets which you could say nothing about. For example, 2, 4 and 3, 5. Which one is greater? Well, right? So partial order, and that would create probably a problem for Hernan. If your relation is a subset relation on sets, min and max of two subsets doesn't make sense. There is an operation, by the way, sort of, which we know that we could, from any two subsets, find a set which is greater than both. What is it? And we could find a subset which is less than both. What is it? Intersection. Any empty set, but it's sort of nice to remember that it's intersection. And eventually you will get to empty set if you are lucky.
I don't think there are too many empty sets.
So therefore, it's a partial ordered structure, but it's also a nice example of something which is known as a lattice. It's good for you to know the word you might encounter in your future adventures. So, okay, so you say it's not
Partial, weak strict order.
because you looked it up.
I didn't look it up, I remembered it, but opening the laptop helped. I imagine Wikipedia and it worked out.
Yeah. So he says, Hernan, do you agree with him?
Wait, what did he say?
Weak strict order.
Weak strict. What does it mean for something to
It's actually, typically you say strict weak order.
Strict weak order.
But
I didn't look it up because
what about non-strict weak order? Would it work? Yes, this is the interesting question. That's the danger of using words without actually knowing what they mean. Because if we knew what they mean, we would know the answer to this question. We would say, of course, non-strict is perfectly fine for me.
I think strict means that every element is comparable.
And you would be wrong.
Okay.
Well, total and partial make that distinction. If it's partial, that means it is not defined for all pairs. Well, it does not.
No, don't. Never mind. Guys, this is very important. So we don't even. This is an amazing thing. We have a room full of highly educated people. You probably even graduated from high school, yes? And we do not know what are the requirements for mean. Isn't it frightening? No, I think it's frightening.
You need to be able to compare the two things and answer the question, which one is smaller.
That's traditional.
Yes, but what if we just throw a coin and answer according whether it's a head or tail? Is it good? It will answer the question.
You can't have both A is greater than B and B is greater than A.
Why not?
Because then there's a problem with ordering.
No,
Let's say
no, there is no problem. Let me give you an example. You see, we have to think about all possible cases. And for example, if somebody comes to you and says, my relation is less than or equal.
But that's not the relation.
Would you draw? Could we talk about mean when we have this?
You'd have to use a different definition.
What do you mean, use a different definition?
And what is the meaning of mean if two things are equal?
Well, you think you guys are very clever. Now, observe. If you have this, you have this.
Yes.
So whatever the meaning. So the meaning that when they're equal, probably you could return either. Probably, I didn't say that.
We were the first one or the second one?
But that applies to this as well.
Sure.
So, what I'm trying to point that when you discuss mean, you could use either reflexive, this is called reflexive, or non-reflexive, in other words, is strict, non-strict. These are synonyms. Synonyms is a fancy word, it means the same. So
a relation is strict if it never holds between an object and itself. So less than does not hold between an object and itself.
but it's not absolutely speaking a requirement for me. Even if you say, but it says in STL book that it is. Because you see, the funny thing, when you try to build a general system, you soon realize that you better pick this kind or this kind. And they are equivalent. So we need, first of all, we need, what are relations, by the way? Anybody know what relations are? What is a relation? Yes.
Don't try to be philosophical.
Yes, no. This is what he read in Bourbakir. He keeps repeating. You could always view it as so. But for simple person, explain it now, so that, like, Jack and me could understand.
Well, two things are either in the relation or not.
which means it's some kind of a function returning.
It's a predicate.
It's a binary predicate, yes. That Jack and I could grasp that. So if you look at two things, it's either true or false. The relation holds or not. Not every relation is an ordering. Right? So what do mathematicians call ordering? Do they have many requirements?
Transitive.
Yes. The only absolute rule for ordering is the requirement of transitivity. That if we have a relation R, and we will know that R of AB, and we know that R of BC, it implies it is transitive. You say, but isn't it too weak? Yeah, it is too weak, but that's the most basic notion of ordering. And it actually immediately becomes confusing because then some very important relations which feel not at all like ordering become ordering.
The empty relation?
Well, let us assume that relation is total. What does it mean that relation is total? It's everywhere defined, yes? So, empty relation wouldn't.
But if the relation was false for everything, that's your predicate, always returns false, then it's an ordering.
That is an ordering, yes.
Or always return
Yes.
true.
And can always return true.
No, that is not.
Of course it is.
It's transitive.
Yes, it is an ordering. Okay. The important thing which follows from ordering, which is one side, is the notion of an equivalence relation. Equivalence relation is an ordering, meaning it is transitive, which adds two other important axioms. Anybody remembers? Reflexivity, which is whatever equivalence might means, Anil is equivalent to himself, according to any equivalence principle. I don't know about Jack. But so.
And symmetry.
And symmetry, not you, but somebody else. What is symmetry?
If A is equal to B, then B is equivalent to A.
Yes, it's symmetric. As it were, it commutes. There's no need to, I mean, there is a thing which you have, let me teach him about math. If you start with A's, B's, and C's, you have to continue with A's, B's, and C's. The second rule is known as quantifier elimination. If you have a bunch of universal quantifiers, drop them all. That's the meaning is that whatever I write applies to everything. So, as we wrote here, we didn't bother to write for any A, for any B, for any C. Quantifier elimination. So, to write reflexivity, we write RAA. This is reflexivity, transitivity, reflexivity. By the way, you would say, oh, which shows that he's not a great mathematician. By the way, really great mathematicians typically would use A, B, C here, and then use some Greek letters here, just to confuse. This is according to a very important book on mathematics called Mathematical Miscellany by Littlewood. It's a very, very funny book. If you want to sort of learn about what mathematics is without learning mathematics, it's probably one of the best introductions. So this is reflexivity. It's only lesser mind like me. Go then and patch it so that you use only A's, B's, and C's. And the third one is going to be symmetry. Symmetry. And while it's not, do we need the implication the other way?
It's implied.
It is implied. Why it's implied?
This is you got a universal quantifier of range.
So you could switch A and B and the other way around. Yes, very good. So this is known as equivalence relation. We will need to remember that. Okay? Give me a couple of examples of equivalence relations in mathematics. What was the first equivalence relation which sort of appeared in mathematics? It was covered extensively in the Journeys course. But you, of course, do not remember a word of what I said there. But once upon a time, there was a great German mathematician, Carl Friedrich Gauss, and he did what? What did he do? He invented electricity. Built a telegraph. This is all true, by the way.
Added the numbers from 1 to
Yes.
He invented modular arithmetic. Right? He suddenly realized that you could take a number line, all the integers, and put them in equivalence classes to define an equivalence relation generated by a number n, any number, for example, 7. And two numbers are equivalent if they have the same remainder, or if they are congruent mod 7, or if they are congruent mod 10. This is a canonical, when you want to think about equivalence relation, again, if A and B give you same remainder mod 7, and B and C give you the same remainder mod 7, say 3, then, well, guess what? A and C would give you the same remainder mod 7. It is an equivalence relation. Now, we have to get back to ordering. In order to get to weak streak ordering, we have to go to really logic. We have to go in a roundabout way. We have to go and define total ordering. Why? Because that's how it happened historically. It's easier to understand something if you first to see one particular example. Because total ordering, amazingly enough, is an example of weak ordering. You say, no, it cannot be. It could be in mathematics, anything else. So, anybody could tell us what total ordering means? It is an ordering, yes? So what do we get? We get transitivity. Then, of course, there is this decision which we'll have to solve one way or the other. Do we mean reflexive or strict total ordering? Because it could be one or the other. Right? So,
but you said they're the same.
they are not the same, but one has we will see that in general. Give us a minute, we'll get there. So, but when we look at ordering, let us make a decision that as our primary ordering, we will use strict. I had to make this decision when I was designing STL, and guess why I picked strict?
Optimization. So it has less occurrences.
Less what?
Occurrences of truth.
One character less. Nicholas is correct. I mean, I had to decide, am I going as a default type this or this? You say, well, Alex, this is not good enough, but they're equivalent guys. Then you could use any decision procedure, such as fewer typing, and I did that. So as a default, I decided that you always define this. Now, if you define this, you automatically get 4 of them. Because now we have to talk about what you could do with a relation. Any relation comes with 3 siblings. 2 brothers and 2 sisters, whatever. I'm not going to go into gender relationships.
They haven't defined total ordering yet.
I haven't. I don't
Just
have that.
want to know.
Yes, but I don't need total ordering to talk about siblings. So, okay, let's assume I have a relation, RAB. Then I have a relation called converse. These are technical terms, and the relation called converse goes both ways. You see? You flip the arguments. So what is converse of less than? Greater than. It's as simple as that. Then there is a relation called complement. What is a complement? It is not negation of R, A, B. Yes? That's a complement. So what's the complement if R is less than? Greater or equal. So this is called complement. These are good words to remember. Remember my diatribe about words being important. That's what enables us to know things. Words are important. It's good to remember. This is converse because we do this. This is complement because we do negation. And then there is a guy here. Or girl. What's her name? Complement of converse. That's the name. It's like mother-in-law.
You also say converse of complement, or is that not allowed?
It is allowed, but people say complement of converse.
Tradition.
No, because they're ordered lexicographic like that. I just made it up. I needed to find a reason why it's complement of converse, not converse of complement. Of course, it is the same. Both this path and this path give you the same thing because this is complement. So this is negation of R, A, B, B, A, word. And what is this relation? Converse. And this relation? Complement of converse. And this relation? Converse. Or maybe this is the converse of complement. Whatever, I don't know. Or this is the same relation as this, yes? So, once and for all, you get one relation, whatever relation, ordering or not. Observe, I never relied on transitivity or anything. You get all 4. Right? And when you deal with total ordering, this I call the primary one and choose this glyph. Why do I choose this glyph, not this glyph? I could have, why ascending order is better than descending order? What logic did I use?
Counting.
Counting. Sort of, what is counting? Let us get to the essence of it. What's the axiom I implied? Which is a wonderful axiom. If I have a successor, successor is greater, successor of x is greater than x. Sort of that it's ordered according to its successive order, right? That your topology coincides with your aberration. And as we will find in mathematics, eventually, this is a very good thing to make your ordering coincides with your aberration. This is how you get to all kind of wonderful things, as, say, totally ordered fields. You could have algebraic structure and combine it with topology by saying that these things sort of work together. I'm not going to talk about that now. So, but I'm still upset because, first of all, he thinks you need to go eat, and then I still did not tell you what total order. We'll get to that.
Yes, but will we get the right name?
Only if we understand what ordering is. Because the question cannot even be posited till you.
I would disagree with that. People, I think, knew what min was before they discovered abstract algebra.
Yes, they did, and they implemented it incorrectly time and time again. That's what I would say. How would I? Because I was one of them, right? In my case, it's more complicated. I actually managed to implement min correctly. It's the max which I screwed up, as we shall see.
So you could do it incorrectly. You could not have this principle, or you could realize that there's a choice and you need to be consistent. Do you know of any system where someone was consistent, but they said no, that greater than is the way to do it, that's the primary relation?
No,
so.
No. Mathematicians, okay, the interesting fact, and this is a philosophy, I mean, I try to do, and this is me, to try to find rational explanation of a common mathematical practice. This is, yes, mathematicians consistently would use that in their books as the primary ordering. When they talk, for example, of totally ordered fields, they write all axioms in terms of this. And I claim it's precisely because that successor being greater is the natural thing. But you will never find it in a math book. So if in some sense, a lot of what I have been doing all my life, I was trying to make explicit the underlying principles of yes, everybody knows what iterators are, but they wouldn't say. So let me figure out what you have to make explicit. So as far as I know, this is a sort of a reliable guide. Otherwise, would I be teaching you something if I thought it was junk?
No, I'm just wondering whether there's that's someone decided that this is the other. Is it convention or is it?
It is a convention. It's a common convention in mathematics. What you would find out that in computer science there are practical people who hate convention of any kind. And when you say, well, let's do this, they say, but we have an immemorial custom at, say, A9, a hypothetical company, and here all of our ordering is the other way around and non-strict, and in any case, we don't need axioms because it's only for ivory tower people. You say, I'm making it up? No, I heard every single word, which I just, from some specific people who are, believe it or not, still employed. So, yeah. So, people make a big deal out of they do not want any fascistic rules like actions imposed on them. They're free spirits. But, you know, I'm obviously this ivory tower fascist. Whatever, so trying to impose, restrict creativity. I actually believe that creativity at that expense is no creativity. I mean, this is a misquote of Barry Goldwater. Some people who know. All right, let's go grab food.